Okay, so the fourth class test was certainly one where I become very aware that the class is now separating out into these two sorts of camps. There are a decent amount of you who are starting to fully understand and come to grips with this chemistry, and you're doing well. And I encourage you to continue with that. But there is still a lot of you who have not yet properly grasped this chemistry, and as such, you're drifting quite far behind here. And this particular test was really just asking some fundamental questions. It wasn't anything particularly difficult, and so it's important that you actually address that in the coming weeks as we move forward. You'll find if you speak to those, if you can identify those who are getting the chemistry now, if you speak to them, you'll probably find what they'll say is that there came a point where everything started to make sense, and then everything just felt sort of easy. It's sort of a logical process. So I want to encourage you to have a look at that. You're going to need to, and I can guarantee you, if you work at this and you understand these basic principles, you're going to see that you will get an excellent mark at the end of this course. This question over here, we're looking at obviously enolate chemistry, and the point is, by looking at these two products here, the one is having occurred under thermodynamic control. In other words, the connection over here would have been via the thermodynamic enolate to give this product, and this one over here is occurring under kinetic control. So the kinetic control is fairly easy. It's always going to be, and it's important that we do this in steps. We have to first add LDA, and one equivalent is the preferred amount. We want to have exactly one equivalent to form the enolate of that. And it's important, if you didn't put this in, you would have lost half a mark. It must be at minus 78 degrees Celsius. All right, because the temperature is just as critical as using a strong, bulky base to form the kinetic enolate over there. And then the second thing is, what is the you add the electrophile that we need to add, and the electrophile is, because this is the bond that's being formed over here, so the electrophile came from the aldehyde of this. Okay, so it would have looked like that. A lot of you got this part correct, so you didn't have a problem identifying what the component is that you needed, the electrophile, to form that bond, but there were many that missed this, and a lot that missed that. This has to happen in two steps. There's kind of a notional third step that needs to happen. We often don't write it up, but it's just at the end when we do an aqueous workup in which we need to add water, and just to protonate this, because if you follow the mechanism, we end up with an O minus. So we need to put a proton there. So we'll add water. Generally, it might be sort of a weak acid that we would have added. But it's stressed that it needs to be a weak acid. We don't have a strong acid, otherwise we could cause this to eliminate, and we get the double bond, which is what happens over here. So this one over here, the electrophile, is hopefully fairly easy to have seen. Again, it's a carbonyl compound, something like that. The formation of the thermodynamic enolate over here was only about 2 people in the class that got this process correct. So yes, the thermodynamic enolate requires a weak base, but the problem is that in order to get the enolate that would form here to react with this aldehyde, they have to be mixed together, and the enolate, if you are using a weak base to form the enolate there, you're going to form an enolate with the aldehyde. And an enolate with the aldehyde is going to cause self-condensation to occur. In fact, that was part of question 3. If we move down to that, at the bottom here, this one over here, one of the problems is we're using a weak base, sodium hydroxide, with propanol, and the sodium hydroxide is going to cause the propanol to self-condense. And so that's why, one of the reasons why this reaction wouldn't work. The other reason, by the way, is that just the sodium hydroxide is going to hydrolyze the the esters over there, so that would be a problem as well. All right, the question didn't ask how to solve the problem; it just wanted to do that. This was actually in last year's one. Okay, so we want the kinetic. We cannot use weak bases. No hydroxide or ethoxide or any of those sorts of things. We have to use. We've got to use a specific enol equivalent here. The best go-to one for thermodynamic enol equivalents is the silyl enol ether. And so the first step would be using triethylamine as the base, trimethyl silyl chloride to get the silyl enol ether formed, and we can do this at room temperature. And the solvent we would use would be dichloromethane. I'm not stressed that you don't put dichloromethane in, but you should be able to recognize it if I write it in. Step 2 is we then add our aldehyde. Am I getting this right? 1, 2, 3, 4. 1, 2, 3, 4, 5. Whoops. Done something wrong there. Okay, we add our aldehyde, and we recognize that this intermediate that formed, the silyl enol ether, which looked like OSMe3, that's that one over there, that this is a very poor nucleophile, so we can't just add this aldehyde, we have to add something to get it to go a bit better. So Lewis acid, if you wrote there Lewis acid, that would have been fine, I would have given you the mark. Just a typical one would be something like titanium tetrachloride. All right, that was the Mukayama-Aldol reaction. And at the end, again, very similar. We need to do some sort of workup with water. Weak acid, weak base would have been fine as well. All right, in all these cases, just so long as the water is important to protonate at the end. Okay, weak acid or base. All right, so that's what we needed to do with that question over there. This is a very typical test or exam type question. This one over here, I was a bit disappointed considering that I told you that this was going to happen. Oh, you're going to get this question, and we'd pretty much done it in the class before. I think what might have kind of made it a bit more difficult is this 9-membered ring. I think people were struggling to draw that out. But essentially, you need to show the mechanism. We've got OET minus. We pick up a proton over there, form the enolate. Recognition that is, if we'd formed the enolate on this side, the ring that would have formed would have been between this carbon, 1, 2, 3, 4, and that carbon would have made a 4-membered ring. By forming the enolate on the other side, I don't even know if I've done enough now. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Put that there. 1, 2, 3, like that. And so we've got the enolate like so. Okay, and then when this reacts, it comes down there, this reacts, and now the numbering is important here. 1, 2, 3, 4, 5, 6, 7, 8, 9. And a lot of people, when they drew out the product of this, they kind of got this all mixed up. But you could remember what's happening is we're forming a ring between 6 and 1, which is a 1, 2, 3, 4, 5-membered ring, and we also therefore have a 1, 2, 3, 4, 5, 6-membered ring on the other side, which of course is what the product looks like this. But we can draw it slightly different. Why don't we just draw a 5 and a 6-membered ring, and then fill in the bits. We know that this must be the new bond. And the new bond was formed between 6 and 1, so we can put 1 there, and we can put 6 there. Now, 1, 2, 3, 4, 5, 6 is the bigger ring. So 1, 2, 3, 4, 5, 6. And 6 goes to 7, 8, 9. 9 is connected to 1, so it's fine. 1 has the O minus, because that happened. Sorry, bad mistake of me. I should have done that in the first step there. And carbon 5 has the carbonyl like that. And now we can see how this relates to that. We have to do, we must get a proton, which will come from the ethanol that's present over there, and we can do ultimately what's an E1CB reaction, so or mechanism. we form that equilibrium and O minus 1, 2, 3 OH, and zoom in there, and that is our product. Okay, so that very elementary mechanism you've got to be able to do that. Okay, so that was the answer to that test. Hope that was helpful to you.